talking a lot about a lot of things kata, and one of the things that we talked about was sharing stories. Thinking, that sharing these kinds of stories will help people to take some of this information and be useful, in their own lives. And so we talked about, coming up with a story, and Kelly has graciously allowed me to use her platform here to share this story, and I think it's a good one. I'm going to talk a lot about some of the work that we did here at Hobson and Mozart to consolidate operations, to reduce inventories, to improve part flow, and it all, it goes to the point of getting to a single piece flow. And so I'm going to show some of the obstacles that I encountered along the way. I couldn't possibly describe all of those obstacles, during that process in a half hour's time, but I'll give you an idea of some of the things that we ran up against and some of what we did to work our way through those problems. And just to give a little bit more context on what I'm talking about when I talk about single piece. So in, true kata fashion, we used a storyboard to talk about the challenge, the focus process, and those conditions that I spent my time working on. My challenge being, wouldn't it be great by June 30th of 2022 that the curve tip assembly process is operating with a single piece flow in a FIFO order and at tack time to meet the customer demand. And so I had a target condition of, achieving a single piece flow through 3 of the operations that you see in that target condition block, being the hole drill operation, the tip weld operation, and the camber operation. The assembly process from cover weld to camber is operating as a cell. The inventory is operating with a single piece flow. The cell operates with balanced labor and inventory to maintain that even flow. And the cell operates maintaining a FIFO order of these materials. I did some other measuring as well, having to do with the cycle times in all of those operations, and I'll talk about that as we go. But in this target condition, my goal was to make sure that those cycle times met or exceeded the planned cycle time that we had based on that tack time of 30 seconds. And in that target condition, we had great success with that. So in the current condition, when I started this improvement work, the assembly process from the cover weld to the hole drill is creating a bottleneck at the hole drill. Cover weld operation is stopping to allow the hole drill to catch up. The tip weld and camber operations are flowing parts at a slower pace, needing to wait for hole drill. The trays used in the camber process are moved on to printing, leaving the cover weld to replenish its trays from storage. There is an imbalance in the labor at each machine. The inventory is moved in a 1,000 piece quantity from the cover weld and a 500 piece quantity through the rest of the processes. And you can see in my exit cycle calculations at the bottom of this block that there's a lot of variation in the process. While the core operation itself is doable, the variation caused us to run over tack time most of the time. So to show a better picture of those two conditions, the current condition and the target condition, I wanted to blow this up a little bit. In this slide, I'm talking more about those inventories that you see between these operations as described in that current condition. There's 1,000 pieces that go through there and wait until an inspection is performed before we move them. And in the hole drill, 500 pieces, tip weld 500, and at the end, another 500 piece inspection frequency where parts pile and wait for those inspections to take place before we move them. And in my target condition, as I've been describing, I was shooting for a single piece flow to be able to move parts through that process sooner than what had been in the current condition. And to support some of what I'm describing here, there's a lot of data that was collected having to do with cycle times at each of those operations. And as I described in some of those operations, that variation was making it impossible, to reach those tack time calculations, most especially in the hole drill cell, and even in the tip weld operation. As those calculations put us over the tack time, there is a clear evidence of work needed, improvement needed in those two operations. And so I wanted to show as well, along with this information, what this looks like in the current condition with the operators running these operations. And I'll talk a little bit about some of the activity that goes on in the hole drill operation. You can see that the operator, even though he's handling the pieces, one piece at a time, he still needs to pile the inventory at the end of that operation into trays. And this is where the inventory sits and waits for those inspection approvals, and he'll pile up 500 pieces at this step. And you'll see much of the same kind of weighting and handling of the material through the welding, the tip welding process. He is handling them one piece at a time through that actual process, but piling those parts into those trays that sit on the table next to him. I'll chance for this video to move a little bit here, and you can see what I'm talking about when we talk about the inventory at this operation. Just to his left, you can see those trays where he places those parts. Same situation occurs at the camber operation as this operator moves these parts through the hole drill, the inspection, the camber, or the deburr operation, I'm sorry, and then into the tray after he checks it dimensionally with a gauge to his left. There is a pile of trays just below that indicator where he piles up the parts and places them, waiting for inspection to take place. So obviously, this is not a single piece flow situation, and we need to do some work to get to single piece flow. So we start listing what those obstacles are. And in this case, my first obstacle talks about that inventory that sits at those operations. I wrote as an obstacle that the currently moving parts from the hole drill to the tip weld requires an inspection at 500 piece count. To move sooner will require controlling parts that does not currently exist. So we had to start thinking about how we were going to approach this obstacle. And I did a lot of thinking about what were we going to do next. And so we came up with an idea, or came up with a thought of why not try creating a controlling card. So this is against that obstacle that I just described. And I wanted to talk a little bit about how that obstacle is written, because there's a key in there that I wanted to make sure that the operators were a part of as well. I wrote that currently moving parts of the hole drill, the tip weld requires an inspection of 500 pieces, and I highlight the word sooner in this next sentence. To move sooner will require control that does not currently exist. We too often make that mistake, that saying that we want to move inventory through the process faster. And I think that sends a negative connotation that operators immediately get stressed about, because that means to them that they have to work harder, and that is not the intent. We just want to move the inventory sooner. So working through this problem, using these control cards enables us to move parts before we hit that 500 piece count, which is where I'm talking about getting them sooner. Creating a control card that contains that inventory, making the move at 250 possible. Just to be noted, I started with these 500 piece counts and I incrementally lowered this inventory. At certain intervals, I obviously didn't go from 500 to single piece flow along the way. Wanted to make sure that everything was going to be done in a more comfortable fashion. And what I expected was to get feedback from the operators and the water striders on the placement and the control of the inventory to change the handling of the material. And what happened was the at-risk control cards, is what we're calling them, were implemented. And the direction was given to the operators and the water striders on moving inventory at risk. With the proper control in place, the parts are moved at a lower count more frequently. The at-risk cards, keeps us aware of inventory that hasn't been inspected yet at this point. And we were able to use those cards to make sure that those parts did get inspected properly before they ended the process. And what we learned was that when the parts are at risk, there is more attention to the quality and the control of the process. So at this point, when we were beginning to lower the inventory and start to talk about getting to a better place of getting closer to single piece flow, my supervisor and I had a discussion about running simulation of the process, because we did not want to alarm the operators in a very dramatic fashion. We wanted to make sure that they were included in the whole improvement process so that they would have some skin in the game and have some feedback to give us. And some of the thoughts that were going on at the time was that we could test the process offline without disrupting the current condition. After all, we had a condition that was working and running, albeit not, as good as it could be, but we didn't want to disturb that while we were running the simulation. We can solicit feedback from the operators that run the process during this simulation, which we did, and was very helpful. We can also observe and correct any unforeseen problems that occurred during that simulation. And we can actually use the product itself, the actual product that we're processing, to support the operator's understanding. There are a lot of different simulations, that people run, and I'm not discounting, using Legos or anything else, to simulate processes. But in this case, having the actual product in their hands, I think helped them understand where we were trying to go. So after running the simulation, we continued, addressing some of the obstacles that we ran in, and I'll talk a little bit about a couple more of those obstacles and what we did to work our way through those. And one of those obstacles had to do with the fixture maintenance at the tip weld being prolonged, causing the operation to run with one fixture at a time, which puts the operation over our planned cycle time. So working on that obstacle, we reviewed the document maintenance steps on the tip weld fixtures for the maintenance improvement. We expect to learn some maintenance steps are simple, and some steps require a higher level of skill to complete. And the information should help plan that maintenance. What actually happened was I met with the tooling maintenance manager to document that tip weld fixture maintenance. The maintenance group then created their reaction plan and documented the steps to the fixture maintenance with a PM schedule. And what I learned along the way, which was kind of surprising, was that fixture maintenance originally for that tip weld is solely dependent on a single person with no written instruction or schedule, relying on one person's knowledge only. And to show you how important that maintenance on that tip welding fixture is I did some measurements. We used data along the way, and as we were making these improvements to support everything that we did. And this is it's clear evidence here of what occurs in that tip weld process operation with having only one tip weld fixture and then having two tip weld fixtures, so that maintenance was demonstrated here with the data as being very important. With one fixture, obviously, we were going over that takt time almost on every single cycle, and having those two fixtures available to run that operation, you can see at the end there what happens to that cycle time. We're able to get underneath the planned cycle time with that pretty consistently. Another obstacle that we ran into during this improvement was that at the hole drill operation, the brush machine and the deburr machine are connected through a program which will not allow running separately. And this prevents the move of the deburr to the camber. This warrants a little bit of explanation. In the hole drill operation, I was looking, as I was observing the deburring operation as part of that, I thought would work better, balancing that cycle time in another piece of the process. So this is what I'm describing here. So with that obstacle in mind, we decided to take that step to decouple that program between the brush and the deburr to move that deburr step to the camber operation. And we expected that decoupling that program will allow that deburr to be moved, and we can then operate the process as described in that target condition. And what happened was that the brush and the deburr are separated. The current condition now has the equipment in place, and today we will run and test the operating patterns. And what we learned was that separating the two machines, the brush and the deburr, was easier than first thought. Knowing this, we can reconnect just as quickly if needed. This is some of the data that I used to support that change of the deburring from this hole drill operation. And with that deburr operation included in that hole drill operation, you can see on the chart on the left, it shows a high level of variability in the process with the deburring included. And when I separated that deburring from that process, the process gets much quieter, much less variation in the process. And with the deburr being as low as it is in cycle time, it was very easy to add that to the camber operation at the end of the process. So what it looked like when I added that to the camber operation is demonstrated in the chart on the bottom, with those two combined still being cycle times being very much below our takt time and our planned cycle time, with a couple of flyers, but nothing that was going to stop the show. So with all of this work that we did, using the data and going through the steps of the experiment and using the operators in the simulations and showing them and training them as to how we were planning on running this operation, we got together with our engineering department and they gave us a floor plan for putting this equipment together. Mind you, these operations were very separated in the room, several feet apart from one another. And after putting this floor plan together and all of the information that we collected together, we got the maintenance department together on a Sunday afternoon and had an electrician here and moved all of this equipment into place. Had an electrician do all the wiring that we needed to make sure that everything was operable. And again, having the operators understand what we were expecting to do, this work being done on a Sunday Monday morning looked like this. The difference between the silos that we had operating in the room and the single piece flow that you watch right now has been profound as far as meeting that customer demand. We have not missed a beat in this operation since, and this is going on a year now. And if you watch very closely, you can actually see these people handing off a single piece to each other. There is a pad on the table where the welder drops off a part. There's also a station just underneath that keyboard there where the hole drill operator drops off a single part to the welder. And the parts are flowing single piece. We collect them at the end of the process and move them to the printer at 250 pieces. That is our boxed amount that goes to shipping from there. So after putting this all together and having these people operate in this manner, there are reflections of my own that I wanted to share. And some of those reflections include that the operators are more aware of the dependence on each other and their roles in the process, which strengthens their synchronization. If quality issues arise, fewer parts are affected. The problem is quickly identified as parts transfer from one operation to the next. Getting the operators involved through the simulation and listening to the feedback gives them ownership of the process. Having the operators involved this way builds confidence for future process improvements, which I think was one of the bigger things that I got out of this. Having people see what was happening and see how we were improving, they would be more ready and able, to take those next steps. So that's my presentation. I hope you enjoyed it.